you can't understand what's coming up if you don't clearly understand what's been said. And I try to really push this. In circuits, you remember, you couldn't do power unless you understood basic Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law. It's like that here, only it's far more complicated in my opinion. Now I'm going to do this. I'm going to first put up some of the important properties, then we're going to look at some problems and try to explore ways to do them. I mean, usually there's multiple ways. And if you have specific questions, ask it, all right? So I'm going to just put them up here. In the book, he has some of them, not all of them. These are the ones that are important. If I have x of at, now, do you remember with Laplace what happens? It's 1 over a, right? Let me get a different marker. Then it's going to be times the magnitude, well, not magnitude, times x of s over a. Here, it would be x and it would be s over a. With Fourier, it's just omega over a. That's a very similar property to that what you had with Laplace. You follow me? Only omega is there instead of that. Everybody with me? So you can use most Laplace transform properties, transfer very well into here. The next one is, oh yeah, this one's not there. This is x of minus t goes to x of minus omega. It's assuming we know this. We know x of t would go to x of omega. That's assumed. For this property, let me just tell you what I'm talking about. If I have x of t here equal to e to the minus at u of t, right? But now I want to know what x of minus t was. I'm sorry, what the transform of this would be. X of minus t would be equal to e to the at u of minus t. Do y'all follow me in this class? Well, what does it say it is? It's just this goes to 1 over a plus j omega, correct class? This would just go to, you make the, whatever omega is, you make it minus. 1 over a minus j omega. Y'all see this? If x of t goes to x of omega, x of minus t goes to x of minus omega. If you want me to prove this, I will, but it's extremely obvious if you just put the symbolism in there. You know, in the definition of the Fourier transform, it's extremely obvious. But I want to show you where this is used. I gave you a homework problem, and I said I wanted to know the transform of e to the minus a magnitude of t, right? Do you all remember that one? That exists for all time. It's not just positive time, right? And what does it actually look like? Well, that looks like this. If this is time, it looks like this, doesn't it? It looks like a decaying exponential from this point, either in the negative or positive direction. Do you all agree with that? Well, how can that be written? Couldn't this be written as, trying to get away from erasing my fingers. This could be written as simply e to the at u of minus t plus e to the minus at u of t. Please look at that and convince yourself that in fact is this, isn't it? When t is negative, then you want at, you want positive at, right? U of minus t is only on for t less than 0, correct class? When t is positive, it's just that, right? What is the transform of this? Well, that's what? That's e to the minus t here. If this is e to the plus t, it's simply 1 over a minus j omega. What's the transform of this one? 1 over a plus j omega. Do you all see this, everyone? Here I'm using that property now. Y'all with me? Let's go ahead and get a common denominator. I want you to see this because this is very useful. If I get a common denominator here, I can say that this actually becomes my x of omega here becomes equal to really a squared plus omega squared, and then I get a plus omega, a minus j omega, or 2a. You all see that? That's the transform of e to the minus a magnitude of t. That's a transform pair. Now I gave you a problem where I wanted the well, I'll get to that in a second, but you all see what I've done there? I'm going to use I need to put duality up there before I do that. The next thing. This is one way where you could use this transform property to really get the transforms quickly. Then I did this too if I had t to the n times x of n right? That's just, when we did it with Laplace, there was a -1, right, squared, or to the nth power, and it was derivative to the nth power of, with respect to s of x of s. Here, it's just going to be j to the n times d omega to the n of x of n, or x of omega, pardon me. And that's really, the most common one is x of t, pardon me, x of t, and that goes to just j, derivative with respect to omega of x of omega. We can do an example of that too, of the property. So if I have over here e to the minus at u of t, I know that goes to 1 over a plus j omega. You all agree with me there? I'm trying to show you how the properties are useful to you, not just put them up there and you don't see where the connection is. You all with me? Now what is this then? What is t in e to the minus at u of t? Well, this is like my x of t, isn't it? Please make sure you make this connection. Doesn't that, that's my function that I know the relationships for, right? Now, when I multiply it by t, what's required over here is I put j times the derivative with respect to omega of 1 over a plus j omega. Sometimes I have to do this because people don't see this operation clearly. Well, this is really equal to j times the derivative with respect to omega of a plus j omega to the minus 1. Isn't that right? Just so you all see what I'm doing here. Now, if I take a derivative with respect to omega of this, here I get j, right? Then I get the minus 1 out in front. Then this becomes a plus j omega to the minus 2, correct? And then I have to take a derivative inside there with respect to omega, correct? Which brings out another j. This is important. So now I can see here, I have j times j, which is minus 1, times a minus 1 is plus 1. Do you all see this? People make mistakes with this one. And it's over a plus j omega squared. So this is going to be simply 1 over a plus j omega squared. Do you all see that? Now, if I wanted, just for completeness, if I had t squared times e to the minus at u of t, what would happen next? Now, I know this is like my new x of t, if you will, correct? Times another t, correct, class? Now take, do y'all say this, by the way? Take another derivative of this, and put a j in front of it, take another derivative. Do you all see what's happening here? And you can continue on indefinitely, but I want to see the progression and the application. Does that make sense? Now the next thing I'm going to say is, oh yeah, we did this one. Let me erase, I'll leave it up there for a second. Next property I'll put over here, and this is modulation. I'm going to put all three of them. E to the j omega naught t times x of t. Then I'm going to put cosine of omega naught t x of t and sine of omega naught t x of t. The reason, and call this modulation. And this is so important. And matter of fact, it's AM, it's amplitude modulation. This is critical. Now, how many remember doing the first one, e to the j omega naught t times x of t, the property? I mean, you at least remember. Do you all remember it? You're looking really sad about this test or something. Is it that bad? Yes. Poor Dr. Noob. He probably didn't mean to make it hard.
No, I don't think so. It was just long.
Okay, well, I'll keep that in mind. I don't know what I can say to him, but I can help. All right, now this is just a shift property. Only thing it does is whatever x of omega is, it shifts it out to minus omega naught. It takes the entire functional form. I want to just do one so you all see it, because a lot of times people say, well, that doesn't mean much to me until I see it applied. And I sort of understand that. I'll get rid of this part. You know, remember how much of a similarity this stuff is to the properties with Laplace, right? Only now instead of s, we have j omega. And most of the time, if you just replace s with j omega, you get the exact same thing. As a matter of fact, you do for all functional forms that are have non-infinite values at 0, and their values are only true for t greater than or equal to 0. Now for this one, well, let me use that one. No, actually, let's do the cosine one for that. What happens to the cosine? Remember how I broke the cosine down into two exponentials and then did it? Because we have that. That just takes it and makes it 1/2. Your book doesn't have this, by the way. I write this down. X of omega plus omega naught plus x of omega minus omega naught. Right? And what about this one with the sine? Now it's j over 2 x of omega plus omega naught minus x of omega minus omega naught. And I proved those. Do you all remember that, class? Those are modulation properties. I want to take one and show you what it looks like in the frequency domain. And this is so important. So if I have a function, and this is a low frequency signal, I like this signal. Suppose I have just e to the minus at u of t, and that's my x of t. I'm going to go ahead and multiply this by a sine. I could multiply it by a cosine. I could multiply it by a simple e to the j omega naught t. I'm choosing the sine. So if I multiply, or better yet, let me do cosine for a different reason. If I take x of t, right, and I multiply it by cosine of omega naught t, well, what happens? That's going to be that's going to be simply 1/2 x of omega plus omega naught plus x of omega minus omega naught, right? Now, the key thing is the spectrum. I'm going to slow down, and I want to make sure everybody sees this. By the way, I didn't put that up there, but this just looks like what? 1 over a plus j omega, correct? All right, now please just hear me. If that is x of omega, then this becomes 1/2. I take my x of omega function, and now anywhere there's omega, I replace it with omega plus omega naught. So that means this is 1 over a plus j of omega plus omega naught. Try to be clear about this, please don't miss this. The next term is what? 1 over a plus j of what? Omega minus omega naught, right? Now let me show you what that looks like. First, I want to show you the spectrum of x of omega, just the magnitude of it. If this is omega here, this function right here, and here this is going to be 1 over the magnitude of a plus j omega. The way you get it is, that's 0. What is the value of this function when omega is 0? Class, just look at it.
1 over a.
1 over a, right? If omega is 0, it's just 1 over a. Do you all agree with that? So it's 1 over a. That's as big as it gets. And what happens? Well, it's got to roll off. It's going to be flat for a while, but whenever this magnitude, whenever omega is about a, then it starts falling off as 1 over the square root of 2. And that's what you normally do, is you put a point here where this is going to be on the omega axis, the value a. And then it will start rolling off like this. Y'all, does that make sense to everybody? If a is 100, when omega hits 100, the value of 1 over 100 plus j 100, the magnitude of that is really 1 over the square root of 2 times 100. It's 1 over square root of 2 times 100, or 1 over 141, basically. It's about 70% of its peak value. And this is x of omega right here. Now, what does this look like? Now when I have this frequency spectrum, what really happens is you take this frequency response right here and you divide it by 2, you put it out to omega and minus omega, and what it'll look like is this. And it'll be divided by 1/2, so the peak value here will be 1/2 a, and it'll just roll down like that. And over here, it'll be the same. It'll be like this. 1/2 a, and it has the same exact roll-off. Do you all see that? Now what it did is took the low frequency signal. It's important to see. It took the low frequency spectrum here and it shifted it and stuck it out at plus or minus omega naught. Do you all see that? That becomes critical. And that's exactly what happens with AM modulation. So for AM radio stations, they're what, at hundreds of kilohertz, right? They take a voice signal. Our voice signal has a maximum, you might say, you can hear up to about 20,000 hertz. I can't. I've been around gunfire and stuff like that. So I can't hear that far, but you can theoretically at least. They'll take a signal that's got a maximum frequency component of about 20,000 hertz, and they'll shift it out to 100 or more kilohertz so that the actual bandwidth here, with respect, if you think about the bandwidth on these things, they're really, this is half power, this is the peak power, this is the half power bandwidth. This bandwidth right here is fractions of the actual carrier frequency. It's very, very small. So you can transmit it on an antenna that's tuned just for the carrier frequency. This little bit of change doesn't change the impedance of the antenna much, and you can transmit it. Does that make sense to everybody? That's how AM transmission works. And we will get to FM, well, that or you'll get it in communications, but that's AM transmission. And all three of these do amplitude modulation. They take the original frequency response and they shift it out to either omega naught or plus or minus omega naught. All right? The neat thing you should remember in the back of your mind is the sine brings a phase change and it's a difference of the two. The cosine doesn't, and you can use that property to determine very accurately a lot of information. I use that in radar with quadrature processing. I can't get into it now, but I'm just giving you a heads up on it. Next property, a couple of them. We've gone over some of these. So what, do you have another test today? You got another one in what class?
Dynamics.
How many have another test today? I don't see a lot of joy for here. I mean, if you're not happy on Monday generally, this is especially sullen for this time of the week. All right, well, it's okay. We'll just have to carry on. Next. Oh yeah, I did this one. I'll put it right here. What happens when we have x of t convolved with h of t? Class? Finkel-Laplace. What happens? Convolution in time is what in frequency? Multiplication of the transforms. That's true. So it's x of omega times h of omega. And keep that in mind. That's useful always. I'll put a few more properties over here. Now I got to tell you, this one is a little tricky to prove. I'm not going to prove it today. But if you multiply the time domain, first I want to do this. Let me put down duality again. Duality says if I have x of t and it goes to capital X of omega, then I can take the form, the mathematical form of this function, and replace omega with t. And then I can take the mathematical form of that function. First I have to multiply by 2 pi, take the mathematical form of that function, and replace t with minus omega. Do you all remember that? Do you remember why that was so useful? There was one thing we did last time where that property really allowed us to solve a problem we couldn't get at with a direct integration. Do you remember what it was? DC. Well, it was used for U of T, but it was when you have just the DC response, a constant in time. If you do the integration of a constant in time of times e to the minus j omega naught t and integrate it dt from minus infinity to infinity, you get nonsense. You get something that's undetermined. Follow me? But if we use duality, we know a delta function goes to 1, right? And again, I'm doing this. If we know a delta function goes to 1, this is so important. You know a delta function has a transform of 1. And we can take 1, therefore, and make that our time domain function. And then out here, I have to take 2 pi, and I replace t with minus omega, right? Y'all remember doing that? Critical that you do. Now, what argument is the delta function of minus omega the same as the delta function of plus omega? How many say it is? And lo and behold, what I can say now is, I have the transform of DC, of 1, right? If this was 2, this would just be 2 times 2 pi. Follow me on this? It scales. That's so important and powerful to be able to do that. And we will use that a great deal. Duality is one of the things I'm going to say. But if you directly apply duality, you won't get what I'm about to show you. Now, write this down. If you have x of t times h of t, remember, this is multiplied in time. that goes to 1 over 2 pi times x of omega, h of omega. It's scaled by an inverse relationship. Now, you're not gonna like that because you look up here and you say, wait a second, I'm missing something. The real problem with this is in the proof, and I'll have to do that at a later date, but trust me, this is right. And it should be in your book, if you look at the properties in your book, if you have your book. Anybody have their book? Not a soul? Okay, well, the tests take a toll. Let's see, I want to put the integral property up too. I want to get these properties up a couple of times. So, first, the derivative of x with respect to t, the nth derivative, do you remember what happened over here? That just became j omega, right, to the nth power times x of omega. Do y'all remember that, class? If we know x of t goes to x of omega, then the derivative of x with respect to t would go to j omega times x of omega. Second derivative would be j omega squared times x of omega. Do y'all follow me in this, class? How many remember that? All right, this is, by the way, this is key. This becomes key. And I'll tell you where you really use it. Think about voltages on inductors and capacitors. Let's do the inductor. The voltage on inductor is L di dt, right? Well, that di dt literally just pops a j omega out in front when you take the derivative, if I is sinusoidal or cosinusoidal. Please realize it has applications to solving circuit problems, and I'll have to show you that. Just remember that one. Oh yeah, might as well put the integral. We did the integral right, x of tau d tau, integrate from minus infinity to t, goes and it has x of omega over, in this case it's going to be j omega. Now that squares with Laplace. Remember with Laplace it's just x of s over s, right? The derivative brings an s out or brings a j omega out. The integral brings it 1 over s or 1 over j omega, but there's one thing else, and it's because these things exist from minus infinity to plus infinity, and they can have a non-zero average power. This is where it comes in. And then you have this. You're going to have plus, and it's going to be pi times x, and that's the frequency domain value when omega is 0 times delta of omega. If you don't understand everything I'm saying, just gather this. The delta of omega turns it on only at omega equals 0, right? It's only at dc. If the x of omega is 0 is the value of the transfer function, x of omega here, evaluated at 0. And the pi comes out because of that crazy duality property where we got the constant over there. If we had 1, it goes to 2 pi delta omega. This is going to be only at omega equals 0, and that will pop out there. All right, now, good. I got through those properties. If I'm talking fast, it's because this is second time through this, or third. Yeah.
So the reason why you had, or is that kind of similar to whenever you do Laplace, you have the plus initial conditions?
We don't have, yeah, but we don't have any initial conditions. These are infinite time events. They go from
Okay.
minus infinity to plus infinity. With Laplace, there are initial energies stored.
Mm-hmm.
These are really more of a, I call this, the way I view this is if you think of any function that is basically on forever, that it has a defined state forever, there's going to be usually an average power that's 0. However, think about this one. Does this have an average power that's 0? 1 is DC, it's on forever. It's got an average power that's non-zero. Do you follow me on that? And it has some amount of power that's there no matter what the time period is you average it over, all right? Here, if you have a functional form x of omega, or I mean x of t, that has a non-zero average power, then you're going to get this, all right? At omega equals 0, you're going to get that value. And that's just the DC power. Think of it that way. It's associated with DC power, it's not actually. We're about to get to that, by the way. And I'm trying to go there without going too fast. Last thing I want to do, the last property that I didn't tell you that's an important one, and I'm just putting them all up there. You've got them in your books. You got some of them. The ones you don't have in your books, the sine and cosine there, put it up there. This duality is briefly mentioned in the text, but it's not shown. Duality is the strongest property, most important property in my opinion, all right? Or make sure you write down duality in your book, right there. The next thing I want to say is, and this comes about, we could prove this literally. I choose to just state it. if you integrate, if you want to see a proof, come up to my office, x of t here. If you take x of t and you take the magnitude squared dt from minus infinity to infinity, x of t, if it is a voltage, the squared value would be proportional to the actual energy. Do you agree with that? All right, if you assume there's a one, they always say, assume a 1 ohm resistor and x of t is either the current or voltage that's driving that resistor. Well, if you want to know how much energy was going to be deposited after all time, you would integrate that voltage and square it, right? Just square it first, then integrate it. That would be the energy. Do you all agree with that? Everybody on this? Well, in the frequency domain, this is equal to 1 over 2 pi times the integral from minus infinity to infinity of the magnitude of x of omega squared d omega. Now, let me just do one of these things so you can appreciate what I'm saying. And I know sullen faces, people that have had a test and feel that evil was done to them. It's hard for you to concentrate, but I'm trying to encourage you, concentrate anyway, despite your licking your wounds feelings. I know that. Let's assume we have this. I'm going to have a voltage plus to minus, and I'm going to say the voltage is just e to the minus 2t u of t. That's a voltage. And it's going to go across a resistor. The resistor is R equal 1 ohm. I can't get any simpler than that, can I? Now I want to find the total energy deposited or better yet, or really I shouldn't use the word deposited, that's spent, for lack of a better word, heating resistor. Well, the way you would do it is, I know that the energy on this case would just be V of t magnitude squared dt from 0 to infinity. You all agree with that? Right? If you take the voltage, square it, divided by R, if R is 1, you get, voltage squared, what is power? V times I, right? Instantaneous. Well, voltage is e to the minus at, right? Current would be e to the minus at times divided by 1, or the same thing, right? Square it, you get that, right? Vt squared, Vt. And that would be equal to the integral from 0 to infinity of e to the minus 2t squared dt. That is equal to e to the minus what? That's 4t dt from 0 to infinity. Do you all agree with what I'm doing here? E to the minus 4t times e to the minus 4t is e to the minus, e to the minus 2t times e to the minus 2t is e to the minus 4t. Now integrate that, and what do we get? We get 1 over minus 4 e to the minus 4t evaluated from 0 to infinity. Correct, class? That's just straightforward. We change these limits, make this 0, make this infinity, and get rid of that sign, change the sign, and I see that this, in fact, is just 1/4 of a watt. Agreed? There's no tricks here. All right? Now, get the same energy, only use this transform right here. This says that is what we did right there. We got 1/4. So if we wanted to do it the other way, then what we do, I'll do it right here. Is say that I know the transform of e to the minus 2t u of t is x of omega is equal to 1 over 2 plus j omega. Does everybody agree with that? Class? All right. Well, what's the magnitude of x of omega? That's 1 over the square root of 2 squared plus omega squared, isn't it? Just take a look. Agreed? Now, if that's the case, what is the energy? It would be 1 over 2 pi, the integral from minus infinity to infinity of this function squared, or 1 over 2 squared plus omega squared d omega. Do you all agree with this? What's wrong?
Is it not minus omega squared? Because you square the j term and.
No, you don't. Remember, we've been through this. It's important you see this. If this is j omega, and this is a, the hypotenuse, the magnitude is square root of omega squared plus a squared. Remember, j indicates a phase of 90 degrees difference, right?
Right.
All right, so you don't square the j. That's a mistake I run into. Yeah.
I'm confused where the square root went when you put it into the integral.
Now, when I square that, right, this is x
Oh wait,
omega
I
squared.
gotcha. That's right.
I'm trying to,
Mhm.
so it gets rid of that square root. Now, when I have that and do the integration, and you can do this, oh, I forgot if this is the, I think I use a secant value here. I haven't done this one in a while. But this, in fact, will go to that value, go to 1/4. Now, frankly, the way you always do it is find the one that's easiest to do, all right? And just use that. And there are certain functions I'm very familiar with integrating e to the minus at squared. That I am. This one you can do, but you need to do a change of variable on this one, or you have to do the trig business. And I think you make a substitution for omega over 2 times, the tangent of omega over 2 is equal to phi, and then you take the derivative of that and you can do it. But I'm not gonna bother with that one. That's one I don't use much. Okay, class? But they're the same. That's just trying to show you that they would in fact work, and you can prove that later. Now, we're about ready to get to your homework, some of the homework problems. I've listed all the properties. I've shown you an application of some of the properties. Admittedly, I'm going rather quickly because the properties, this is the second or third time with Fourier you've been exposed to them, and you've been exposed to them with Laplace already. And you have them in your book. You're going to need to know the properties very well. So one of the problems I gave you, I wanted the transform of x of t equal to 1 over 1 plus 3t squared. Do y'all remember that one? That exists for all time, by the way, right? Now, off the bat, if I have to do the transform of that, that's some pretty rotten math. I have that times e to the minus j omega t, then I have to dt it and integrate it. It'd be a mess. Symbolic integration on your calculators does help with that. I don't know if it can do this one, I'm not sure. Symbolic integration does have limits, but it can do a lot of them. But if you think about this, there are certain things that we just did that allow us to do this. And we're going to make use of both duality and another function. Remember I said that e to the minus a times magnitude of t went to 2a over a squared plus omega squared. You all remember that one? Right? We know that. We see something, or I see this. It has a very similar form. It's a t squared here, it's omega squared here. The other terms are constants, are they not? So let's think about this. If I have this goes to this is my x of t, this is my x of capital omega, correct? Please be attentive here. This is the kind of problem I give you routinely. They're more difficult than before. They're going to be at a level above. So you have to be sure you understand duality and the transform pairs that are standard. Now, when you take a look at this to this, take this to the time domain. What do? I have 2a over a squared plus, what do I replace omega with, class?
T.
T, right? You all remember? Sure, this becomes t squared. Over here, what do I have to do? First thing I do is write what? I'm going to get you making sure. 2 pi. Have to put the 2 pi in here. Now I take this function, which is my x of t, and I replace the t with minus omega. So it's going to be e to the minus a times magnitude of minus omega. Do you all see that? What is the magnitude of minus omega? Just put magnitude of omega. You don't have to make it ugly, right? All right, now, if we have that, let's see if we can fit the form here. Let's see our form. The key thing is, I'm going to square this out first. Here's how I'm going to do it. I'm going to say I have really 1 over 1 plus 9t squared. Do you all agree with that? guys? Now I want t squared by itself to fit this form, right? So I'm gonna divide top and bottom by 9. So this is gonna be 1/9 divided by 1/9 plus t squared. Everybody got that? Please make sure you're attentive here. This is a trickier problem. I said this is a more difficult problem if you read the homework, right? Now, what do I see here? I'm trying to fit this form. Y'all see here, my a squared is equal to 1/9, and therefore my a is 1/3. Do you all agree with that? Correct, class? So now I know that, and that means now I can say that with that in mind, I'm trying to do this, what's the easiest way to do this? I have this. I have 1/9 plus t squared, but I need a 2a up here. Well, my a is 1/3, right? Correct, class? 1/3 would be up here. That would be a. When I multiply by 2, it would be 2/3, correct? You agree with me? That would give me this 2 pi e to the minus, and this would be 1/3 magnitude of omega. But we're not quite there yet, because what did I actually have? I had a 1 there, didn't I? I didn't have 2/3, I had a 1. So I have to multiply this by 3/2 and multiply this by 3/2. And now I can say, in fact, this becomes 1, and I can get rid of the 2's, and I have this. And I can say, in fact, the transform of, wait a second, I'm sorry, I gotta get the 1/9 first. Let me do this again. I know that when I have 2a over a squared plus omega squared, that came from really, or I'm sorry, 2t squared, 2 plus t squared, here, that goes to 2 pi times e to the minus a times magnitude of omega. That I know, and now I've got to fit the form there. So the first thing is I replace this with 1/9, and I replace this with 1/3. I'm sorry about that. And that means this becomes 1/3 as well, right? And then to get that, I have to multiply. I want the 1/9, I'm sorry. Oh, my bad, I want that. If I want 1/9, I have to take this and first multiply by the inverse of 2/3. So I multiply by 3/2, and then I multiply by 1/9, right? And the 2's would cancel, and then you would have finally 1/9 over 1/9 plus t squared would go to, and this would be, that's going to be pi over 3. E to the minus magnitude of omega over 3. You can check the solutions. This is a more complicated problem because you got scaling involved too. Y'all follow me on this, class? How many see exactly what I'm doing basically? I'm trying to fit form. It gets irritating just for the level. Here's what I mean, I basically knew this transform pair here. Now I have to make that fit the one I had. So first thing I have to make that fit. So I have to divide by 1/9, right? Then after that, I have to have the 2a up there as well, effectively 2a. Look through that. Next thing I'm gonna do, I've got a bunch of little things. That was one of them. Were there any questions about the homework, by the way? There were several harder problems. I'm gonna do the other one. I had one where I had two sinc functions basically multiplying each other in the time domain, right? Let's just do that one. Do you have the homework in front, available? No. Here's what the function was. This is a harder one, but this does appear on tests. The sine of pi t over pi t times, and then it was the sine of 2 pi t over 2 pi t. Y'all remember that? And they wanted the Fourier transform of this. Well, this is one, trying to do that transform by itself would be a nightmare. Here's where you start. Do you all agree that if I had a pulse function of with tau of t, that would go to simply a sine of, well, I'll put a sinc function, sinc of, and this would be tau times omega over 2. Do you agree with me on that? Right? Now, this is really equal to the sine of tau omega over 2 over tau omega over 2. Do you agree? Class?
Isn't there a tau out front?
Times tau, you're right. You're absolutely right. Absolutely right. Times tau. Trying to get this one in, it's going to be tight. So that's a sinc function, and this is a sinc function reduced to an argument. If I look over here, what do I really have? I have this, looks like the sinc function, right? Of pi t, and that looks like a sinc function of 2 pi t. Well, just for the arguments, because the definition of a sinc function of x is equal to sine of x over x. So here, this is a sinc function of pi t times another sinc function of 2 pi t. Now, when I'm going to go to the other domain, what I can do is this. Please listen. You see how I know I have this relationship, right? Let's use duality on it. Please be attentive here. This is important. So if I use duality, I can say I take that functional form in the frequency domain, my x of omega, and I replace omega by t. So now I have tau times the sinc of tau times t over 2. I've taken that from the frequency to the time. I'm using duality, right? The mathematical form of the frequency domain transform I use, and I replace omega with t, and I take it to the time domain. Now over here, I take this functional form, but before I do, I immediately multiply by 2 pi. And now I take that mathematical form, which is there, tau times that, and I replace omega with I replace, it was backwards. I put the 2 pi, sorry about that, and I take this mathematical form, and I replace t with minus omega. That's my point. I'm sorry about that. You agree with me? I still got time, right? All right, now look. Isn't p tau of t an even function? It means all values for, if I have p tau of minus x, it's p tau of x, correct? Correct, class? So I can get rid of that minus. That's an even function. Do you agree with that, everyone? I can get rid of that. Now I have a property, right? Take a careful look at this. I would like just sinc here, right? So what do? I divide this side by tau. I would like the transform of sinc, right? And look, this is multiplication in time, is convolution of frequency. But the convolution isn't that bad, thank God. This is one of the times it isn't. Do you all agree with that? Now let's do this. First, my first one, I want the transform of sinc of pi t. So the sinc of pi t goes to what? Well, here, what do I know? I know tau over 2 is equal to pi, don't I? Look at the argument. Agreed? And that means tau here is 2 pi. Now it can come over here, and I see 2 pi divided by 2 pi is 1, right? And then I have P, the tau is 2 pi of omega. So that's the transform pairing for sinc of pi t, correct? Next, what happens? When I have sinc of 2 pi t, what goes on? Well, now my tau over 2 becomes 2 pi, and therefore tau is 4 pi. Do you all agree with me here? It's just looking there and equating things. The coefficient of t is tau over 2, and in my case, the coefficient is 2 pi, right? What about over here? Now it becomes 2 pi divided by tau, which is 4 pi, times p, the width of this is 4 pi of omega. Now 2 pi over 4 pi is a half. So now I put a half down. Now I know the relationship. This goes to this goes to this. So multiplication in time, if I wanted the transform, would be convolution in the frequency domain. Do you all agree with that? I'm going to put that up here. So now my answer would be p of 2 pi of omega convolved with p of 4 pi of omega. Just about out of time. I don't have time to do that convolution, but you see these are boxcars. Do you all see that? When you got boxcars, they're easy to convolve. I'll finish this up, but you can just think about,
Would we like need it in the convolution or like?
Yeah.
Okay.
You have to do it. I mean, you can't get the answer without doing it, right?
Okay.
Now, I know it seems like a lot of steps, but the more of these problems you do, the quicker you get to the end. You'll see the steps you need to go through, and you'll go a lot quicker. I'm taking a lot of time right here, developing this how to use duality, and that's what you haven't seen yet. I want to make sure you see it. I'm going to give you some homework. I know you've got tests this week. I heard 4 tests from somebody. I don't know how many tests you got. But on Friday, we're going to get a short quiz related to this. Please try to at least carve out an hour or 2 a day to do these things. It gets harder, by the way, not easier. It gets more complicated. But it will be a lot easier if you stay up with this because there's a lot of redundancy. There's a lot of similarities. All right, see you next time. Good luck in your next set of tests, whatever they are. Dynamics?
Dynamics, yeah.